And then, of course, yeah, we are trying to find the policy that will optimize, maximize that value. I imagine yesterday probably you saw cost to go, right? So reinforcement learning, we typically have rewards rather than costs. And so we're maximizing rather than minimizing. But all of this boils down to more or less the same thing. Good. All right. Yeah. So then we also get this notion. So indeed, you have this cost to go function. That's typically called now the value function in reinforcement learning lingo. And so now the idea is that somehow we might care about what rewards we're going to get after some time step t. Or if we're in some particular state at some time step t, what is the expected return from that moment on if we're going to follow a particular policy? And that's really what this value function expresses, v pi of s, the notation here. All of this clear so far? Good, good, good. All right, so yeah, then putting it together, we get this MDP framework, right? So a set of states, set of actions, transition function, which has the Markov property, reward function that has the Markov property. Yeah, there's some different ways that you can try and write these things down. So the latest version of the Sutton and Bartow book won the ACM Turing Award last week, the week before. Anyways, they had this kind of notation that generalizes this. There's a distribution over next states and rewards. So then you can also have stochastic rewards. So some different ways that you can write these things down, but more or less this all boils down to the same thing. Good. So then how can we somehow now compute these policies, right? And yeah, the easiest way to think about this is by what I like to call finite horizon dynamic programming on trees. And then a student or TA of ours found this nice picture to go along with it. Yeah, right. So okay, so the idea is so suppose that we're in the simplest possible setting. Some horizon t that we want to make want to decide on actions for some number of time steps. So you can think of this as, well, the problem really just is t time steps, or we're just gonna decide for the next t time steps, right? Somehow do this type of online planning where we observe the state, then we construct a plan for t time steps. Execute, perform the action, and do the whole thing again in the next loop. What we're just going to do is apply this basic notion of maximum expected utility. That's really just all we're really trying to do, typically. So how does it look? Well, we can just think of this kind of tree, where this is the state now. We can think of the actions that we could take. And then we can think of what those actions could result in, right? So these are stochastic transitions, and then repeat, right? Somehow just fold out the look-ahead tree of things that can happen in those next t stages. And then perhaps we have some rewards here at the end, some terminal rewards, and then we can just try and compute now these values, right? So clearly, if we're at the end in state A there, then the value is going to be 4 because we're going to get reward for that. And so then we can just somehow work out what is the expected reward, right, for all those little square nodes. So here, the expected reward might be somehow that 4 times, well, a probability, apparently 0.8, something I cooked up here. And the other outcome is 2, with a probability of 20%. And so the expected reward might be something like 3.6 there. Right, very simple. And of course, you can do that then everywhere in the tree. So at the square nodes, we take these expectations. At the round nodes, we get to choose. So of course, there we're gonna maximize. We're gonna pick the things that maximize our values. So in this case, well, we will take action A1 if we end up there. And then, of course, you can do that in the entire tree and somehow then figure out, what's the best action to take now and indeed engage in its online planning. Or if you computed this and it's really just a T-step problem, this is really specifying what you need to take in all different cases. All right, yes. So, of course, this is not very practical because this tree gets very big very quickly. All right. So yeah, you can think of more sophisticated solution methods that I will not cover today. Monte Carlo tree search, these type of things. But we will just consider perhaps we can somehow cache the results, right? Somehow there's all kinds of different ways. Certainly in this example, to get to either state A or state B. And I just told you that the history doesn't matter, right? So somehow, perhaps we should be able to do some caching or reuse some of these results. Right, and so, yeah, we can do that. Essentially, you can think of this by, conceptually, we're going from this sort of tree representation to a directed acyclic graph, right? And okay, so I've now rotated the thing. So now the last time step is on the right-hand side. And we're going to work our way back to time step 0 on the left-hand, right? And it's going to look very similar, right? So somehow here we have our +4 again and whatever outcomes. So again, we're going to have the square nodes that correspond to those Q values, right? Where we take the expectation, and then the round values where, again, we're going to take the max, right? So we end up with something like this. But now, of course, we can also do that for the other round nodes, and they will somehow point to the same states, right? Rather than somehow splitting and really making this huge tree. And of course, we can then just do that for every time step, right? And so by doing it this way, rather than now having this exponentially sized tree, yeah, you just get something of order, well, number of states, right? It's the amount of work here. Times the number of time steps. And of course, like if you can get from this state to any state, the total complexity is going to be quadratic in the number of states here, right? Okay, well, so far, hopefully simple, right? It's really not too much fancy stuff going on here. We're having this MDP, and we're exploiting this Markov property to perform dynamic programming, right? It's just the basic idea of dynamic programming. We can split problems by somehow dividing them into sub-problems. Well, clearly the sub-problems here just are, what's the value for a particular state at some time step, right? And that I can reuse because I can visit that via many possible routes that I can take. Good. Yeah, that's really all. I guess also that's on this slide. Nothing more to really say, I think. Okay. Oh yeah. This is somehow perhaps nice still to try and do. Just I didn't set up any online polling thing for this. But perhaps thinking about these questions is nice, and we can somehow talk them through. So which of these are correct? Dynamic programming exploits temporal structure. Dynamic programming on trees depends on the Markov property. Dynamic programming on DAGs is linear in the horizon. And dynamic programming is linear in the number of states. So yeah, I think I probably already spoiled most of this a little bit if you were paying attention, but let's just try and go through them. Dynamic programming exploits temporal structure. Who agrees with that statement? Yeah? Anybody who disagrees? Oh, well, one person here. What is your reason to think to perhaps disagree here? I see, I see. So your reason is like, well, because you make explicit all the states, yeah, really you're not only exploiting time, you're exploiting much more, perhaps, also those states. Actually, that is a reasonable answer as well. I mean, I would say yes, it exploits somehow the temporal structure, but you are right. It does so by conditioning on much more than the time itself. Right? Yeah. Okay, dynamic programming on trees depends on the Markov property. Who thinks that that is the case? A few, I think the minority perhaps. Who think that is not the case? Also a few. This one's more tricky, yeah? Yeah. Okay. So actually, the interesting thing is, of course, if you have the tree, any node implicitly encodes the past, right? So actually, it turns out that you can do the same thing also for POM-DBs later. In cases that the state does not have the Markov property, because somehow the path encodes the past. But then, of course, the follow-up question, if you do the DAG trick, are you then exploiting the Markov property? Yeah, right? So the tree we can do also if the state does not have the Markov property, but the DAG is really specific to having the Markov property, right? Because it matters otherwise how you got there. The DAG encoding saying it doesn't matter how we got there. That's precisely what we're exploiting. Good, good. Yeah, dynamic programming on DAGs is linear in the horizon. Yeah. I think most people are saying yes here. Who disagrees with this? Yeah, okay, curious. Can you say why? Yeah, yeah. In the tree case, yes, certainly. I'm talking here about this DAG case. Yeah, no worries, no worries. I'm guessing it's also perfectly allowed. Yes. The height of the tree also is indeed linear in the horizon. So you just have one level for every time step. But yeah, it blows up, right? Yeah. Yeah. So yeah. Oh, okay. Yeah. I guess indeed it's what how do we interpret what this statement means? But yeah. And then dynamic programming is linear in the number of states. Who thinks that's the case? Nobody. Oh, that's good. Because yeah, it's not, right? Like if we have the tree, it's gonna be actually somehow exponential in a way. And if we have the DAG formulation, it might still be quadratic. What I said, right? Okay, good. Then. So this was for a finite horizon problem. Of course, we also would want to be able to deal with infinite horizon problems, right? And like I said, we'll focus on these discounted MDP settings, where we want to now compute a policy that optimizes a value function, this V of pi. And the recipe that we'll follow is that of a policy iteration or generalized policy iteration. We'll talk a little bit about what is generalized about this later, or about how it can be generalized. And it's a very simple recipe. It's essentially we pick an arbitrary policy pi. We're going to compute its value function, v pi of s for all states s. Then we're going to use that value function to do policy improvement. So we're going to find a better policy, pi prime. And then we're going to repeat this. Right? Very simple procedure. Was there a question? No. All right. So if we want to do this, we need to somehow compute the value of a policy. We need to do also called policy evaluation. Right. So we're going to consider now the setting where somehow the action is going to be fixed. Right. So somehow if we specify the policy, essentially, we know what action is going to be selected for each state. And so we can actually just ignore the actions completely to some extent, right? We just take the part of this transition function corresponding to the action that we would select. Does that make sense? So we can just think of this as a Markov reward process, this is also called. It's just a Markov chain, it evolves. There's going to be rewards emitted at every time step. Things are going to be stochastic, but we can ignore the actions just for a little bit. Right? Okay, good. So then how can we compute the value of a particular policy? Well, given what you've seen yesterday, all of this should be relatively simple. Right, like I think yesterday probably you saw the Hamiltonian Bellman equation. We're keeping it much simpler here. We're just in this sort of discrete state, discrete time setting, and in that case, the value function satisfies this simple Bellman equation. It's just saying, well, the value for being in a particular state when following policy pi is this expression. So here, this allows for the possibility of the policy being stochastic. I said we don't need them, but you can still possibly consider this. So you take an expectation over the possible actions, and then you're gonna look at, okay, what's then actually the value for that particular action? Well, you take this expectation of possible next states and rewards, given the current state and action that we, are considering taking here, or that policy is specifying with some probability. And then this is really where the value comes in, right? So it's the reward itself plus gamma times the value of the resulting next state S prime. Right, so just a recursive expression that just, specifies this expected value as, okay, I'm going to get the reward now. And then, of course, at the next time step, the expected sum of rewards is that value again. Okay, well, so then how can we solve this? Well, there's two real options. One thing is just, this is a linear system of S equations with S unknowns. So you can just somehow, in MATLAB or whatever, do this \b or something, right? Like, I don't know what it is in NumPy, but so you can just solve it as a system of linear equations, right? Because the values are the unknowns. But the policy we said was specified, so we have their probabilities. The MLP, we assume, is fully specified, so we have these probabilities. You can just somehow write it out. The other thing, which is always a little bit more, easy to wrap your head around, perhaps, or more informative to look at, is this iterative policy evaluation. I have this kind of like nice example where you can work through some of these steps, but I decided to skip it perhaps for this lecture. I imagine that the slides will be made available or have been made available. So at the end of this, you can see that example, I think. Oh yeah, here. Well, okay. So like I said, there are some different ways in which you can specify either the rewards or the transition probabilities, etc. And so all of them, they lead to slightly different formulations, right, of this Bellman equation. So somehow ranging from, I think this is the one, the most general one to some extent that we just discussed. Then here, if the rewards are of this particular form, deterministic, you can rewrite it like this. If you have rewards that only depend on state and actions, you can rewrite it like this, right? So somehow you don't need to put the reward inside the expectation over next states anymore. And you can always, by the way, if you have this type of reward, you can always rewrite it like this. Right? As long as you care about the expected value, you can actually always do that trick to some extent. And then, here, if we have now a deterministic policy, we somehow just plug in, okay, the actions that we're taking for the state S and here as well. So we get rid of this summation over actions. Just somehow different ways that you can rewrite this. Okay. So how does this iterative policy evaluation then work? Well, it's really super simple, right? It's the idea that, okay, we're gonna somehow fix the policy to evaluate, and then we're gonna take this Bellman equation. So this is now the simplest form here. The simplest form of this Bellman equation, because that apply to our particular problem. If, somehow you have the stochastic rewards, etc., you need to use the other form. But yeah, doesn't matter. We take the form that we think we can use, and we turn it into an update equation, right? Why does that make sense? Well, we're looking somehow to for this value to be satisfied, right? This equation to be satisfied. And the idea, of course, is we just start on some arbitrary place and do these updates until we somehow converge to a fixed point, right? And will that happen? Well, yes, this will happen because this is a contraction mapping, etc. Not certain if that type of thing was also discussed yesterday. I wasn't planning on doing that now, but yeah, you can somehow show that this will converge, right? So really, we just initialize our value function v0 in some way. Perhaps 0 for all states, that's very typical, or some random noise or something. And then you can iterate. Somehow vk is given, and we compute vk plus 1. By somehow, just sweeping over all states S, and just computing that formula. Right? So involves doing, of course, a loop over next states S prime, again, still quadratic, but possibly, if you can go to all states, you can try and exploit, of course, knowledge of reachable states. Okay, so if you indeed initialize to 0, then essentially you can compute the sequence v0, v1, v2 that then really correspond to the step, the sequence of k steps to go value functions, right? So v2 then is the 2 time steps left to go value function. And if you iterate this will somehow converge to the infinite steps to go value function. Right. Okay, so this is somehow this example. Oh, it's actually still in here, but I was going to skip it, like I said. Or I guess perhaps I skipped some steps, but I think this is relatively clear, right? Somehow, we have this little MDP, so terminal state here. You get 10 when you transition to the goal. This is how it's set up. You need to be always a little bit careful, but okay, so then you get the 10 there, and then somehow you're gonna compute the rest of the states and converge over time by just applying this. Okay. Yeah, in this kind of procedure, so I said, well, you're gonna compute this sequence of k steps to go value functions. So that's true if somehow you have, say, the value of some state k in some array or something. And then I have a different array in which I compute the values of that k plus 1 to go value function, right? And then I have yet a different array, or I take the first array again to compute the k plus 2 value function based on the values of the other one. That's conceptually nice and pleasing. Of course, you can also try and just have one array and just do it in place, sort of. And turns out that's even better, right? So you just, so you no longer then have this correspondence to, k steps to go value functions, but you're already using updated information, and that's only better to do. Of course, the ordering then really determines what your results will be at some stage k, but it doesn't really matter because you're only really interested in what happens in the limit. You don't care about that. It's a good question. Why can this be faster? So it really has to do that you're gonna use a value that has already been updated, right? So you're really just making use of already newer information, if you will. So somehow the whole idea, of course, also starting from that DAG view, right? The dynamic programming view, is to get the information from the one side all the way to the other side, right? And somehow, if indeed in doing an update, you can essentially skip a step, because that's more or less what you're doing, right? Yeah, then you're propagating that information more quickly. Hope that makes some sense. That's, yeah, the best intuition I can give, I suppose. Yeah. And then there's also, you know, things like indeed trying to figure out actually in what order you process the states, right? If you select a smart order to process your states, you can also, yeah, much better perhaps propagate some of that value, right? So imagine indeed we have a grid world. There's some particular goal, and you know, we're starting somewhere. So if we somehow process the states towards the goal, then we're not really, you know, taking advantage of the structure of the problem. While if we are somehow processing them in the other way, right? Somehow, yeah, we first do the goal and then the one next to the goal, then that has the correct value. And then we do the one next to that, then that has the correct value. So then we can, you know, very, very nicely somehow compute those values. So yeah, somehow this ordering, how you process the states might matter if you want to get this quicker. Good. Okay, well, so this is now a way to compute the value function, right? And I said we're gonna do this policy iteration. So that means that now we also need to do this policy improvement step. Good, right? So yeah, we have policy evaluation, policy improvement. So how do we do the policy improvement? Well, for this we make use of this this Q function that we've already seen before. It's essentially that expected value associated with those square nodes, right? And so somehow if we computed v of pi, then usually we have already, you know, as a side product computed these Qs. But you know, suppose we didn't store them, then you know, we can recover them by applying this equation again, right? Somehow we have the v pi's, and we can just now compute the expected value for taking action A now, and then following policy pi again afterwards. Right, so this Q value, the action value function, really corresponds to this value of doing this one-step deviation of your policy. What happens if I don't follow policy pi starting now? I first will do action A now, and then I will follow policy pi again after. And yeah, clearly the idea is that, well, if it's beneficial to deviate now from the policy because there's a different action that will give actually a higher value than what my policy is getting, well, then perhaps I should just do it. All right? And that turns out to be indeed correct in MDPs. Yeah, okay, so again, this relates to, you know, somehow having those different forms of MDPs leading to different forms of value functions. And you know, if you have a simplified problem, you can use perhaps something simpler. But yeah, this is just the part of the value function is after the expectation of actions, essentially. Okay. So yeah, now we can improve the policy. Oh yeah, question? Yeah. Between Q and V, you mean? I mean, they are very similar, I would say, actually, right? It's really somehow, so this is the value that you expect to get when you're in state S, when you follow pi, because you're going to take the expectation of actions according to pi, right? And here we're saying, well, we're just going to take action A first, no matter what pi specifies. So that's just the difference. Yeah, I don't know, like whether that's the answer you're looking for. So this action, okay, so this Q function specifies these values for all states and all actions, for all S and all A. Yeah. So that's important to get clear. Yeah, you should need perhaps have some quantifier or something. Oh, yeah, it's good question. Yeah, any more questions about this? Then, yeah, we're now going to use this Q function to update our policy, right? Because we've computed this QSA for all states and all actions, what we can do is for all states, here it actually is, now select the maximizing action, right? Just look at, okay, what is the Q value, the action value that will maximize my expected return at this state S. So we're just being greedy. And that's really it, right? Now we have a new policy. The policy changed. And we can do policy evaluation again, and then policy improvement again, and then policy evaluation again, until this is going to converge. Right, will this converge? Yes, it will converge. Oh yeah, so here was also kind of like an example of this. So somehow, okay, we had the previous policy here, you got -10 here because you got stuck in this infinite loop. Now we look, we compute these different values. So yeah, whatever, you know, if you go north, we're gonna still get -10. If you go south, you will still get -10. If you go west, you will still get -10. But now if we go east in this location, we're gonna get +8, right? So yeah, then we somehow switch the action. And you're gonna get +8 point. Yeah, so does this converge? Yes, it will converge. Right, so this is great. Given that we will only visit, in this case, you know, if we do this greedy update, we will only visit deterministic policies. There's a finite number of them. So yeah, this will converge in finite time as well, right? Provided that somehow these policy evaluations we wrap up in finite time too. Right, and then it's going to converge to, yeah, really the optimal thing. So here we get the typical star equations, V star and Q star, so that the value of an optimal policy, the action value of an optimal policy, yeah, they specify. So I always distinguish these Bellman equations that hold for any policy. These are the Bellman optimality equations, right? The ones for the optimal policy. There can be multiple optimal policies. They all share the same optimal value function. Right, so that's also kind of like, or in these grid world types of settings, yeah, there's just, you know, particular values that have the same expected value, right? Different actions that have the same expected value. So you can either go up or you can go right. You will both to the same values. Yes, question. Yeah. So yeah, good question. So the question is, yesterday there was an example where the values and therefore also the optimal actions depend on time, right? If you have a finite horizon, indeed that may be completely the case, right? Somehow, yeah, you only get the reward when you get to the goal, but perhaps there's not enough time steps left to even get to the goal. And then you might not even want to spend the energy, right? Perhaps you also have a slight negative reward for every step you take corresponding to, yeah, just fuel use or something like this. And then it would actually be optimal to not move towards the goal if, yeah, there's no longer any chance to actually get there. So yeah, that's really a difference between this infinite horizon setting and a finite horizon setting. In the finite horizon setting, you really want that sequence of value functions that you would compute if you use the two arrays, right? Then you also asked something else. Sorry, I'm only partially answering, I feel. Yeah. Okay. So the question then, I suppose, is how do we use these type of methods to compute the optimal policy in a finite horizon setting, right? And I think, yeah, the answer is that you can think of that finite horizon setting as a setting where we have a augmented state space, right? So a state corresponds to, well, what is the actual state of the system and how many time steps are there left to go, right? So if you have that type of state encoding now, you can think of it as a infinite horizon problem and could still apply this. Of course, then what's going to happen if you do the value policy evaluation is that one policy evaluation is going to somehow compute the values for all the different time steps, right? That makes some sense. Good. Yeah, I hope everybody got that or was not confused by it. But otherwise, let me know. But it's a good question indeed. That's how somehow do these infinite horizon settings and finite horizon settings relate? And it's indeed really the case that a finite horizon setting is quite different from an infinite horizon setting. All right, let me see how, yeah, well, I should be okay. So I have until 10:30, I think. Yeah, I think we should be roughly good. Yeah, oh, yeah. So this generalized policy evaluation then, or policy iteration, what do we mean with this? Well, now, of course, now we do this policy iteration. We have this policy evaluation step, which indeed can take perhaps a long time, right? So I didn't give all the algorithmic details, right? But typically you specify some epsilon, somehow yeah, say your tolerance level or noise level or somehow, the accuracy within which you would want to have your values. And then you do these iterations, right? These sweeps through the state space to do these updates. And then if the results don't change more than epsilon anymore, then you kind of stop this procedure. But that can take some amount of time, right? Could depending on your MDP, take quite a few sweeps. And so it's going to slow things down. And so then a question is, do you really need to run that policy evaluation until convergence? Because perhaps, already becomes quite clear relatively soon that some other action is looking pretty good. And that's kind of like the idea of generalized policy iterations, kind of like, well, if we somehow truncate this policy evaluation or approximate the policy evaluation, perhaps we also approximate the policy improvement, right? But somehow if these two processes now become approximate, yeah, generally it will still kind of work, right? Of course, you need what is approximate. If it's kind of like really wrong, then it will not work anymore, right? But if there's some good reason to believe that you're making steps in the right direction, yeah, you're expected to somehow converge. And this is, quite important in the reinforcement learning setting, where a lot of these algorithms actually are based on this underlying principle, right? Somehow there's some amount of policy evaluation going on, some amount of policy improvement going on. Yeah, right. That's this notion of generalized policy iteration. And so there's a particular example which is called value iteration. That's actually perhaps even more famous algorithm than policy iteration itself, right? So value iteration is a instantiation of this idea of generalized policy iteration, where actually you only will do one policy evaluation iteration, right? Only one sweeps through the state space. And then immediately you do the policy improvement. And so then, you can actually combine them in a single update rule, this improvement and the evaluation, right? What happens is you're going to make sweeps through the state space. And at every time you just apply this equation, right? You're going to do the maximum over actions, so it's a loop over actions, and then compute this expected updated value, right? It's one step of the back propagation step. Right, and then yeah, you apply this just repeatedly, sweeping through the state space, and again, it's gonna converge. Okay, yeah. Well, so far we've dealt with MDPs. Because these problems are stochastics, we will need feedback plans typically. And then to compute those feedback plans, yeah, we've been discussing variants of dynamic programming, some for finite horizon problems, some for infinite horizon problems. We even discussed how you might use those infinite horizon methods to deal with finite horizon methods. Basically got to this generalized policy iteration paradigm. Good. Any questions up to this point? And then, I don't know, I'm thinking, I think I should probably have enough time. Perhaps we should just take 2 minutes to, you know, think about nothing and relax our brain for 2 minutes, because it's a long time, 90 minutes non-stop. Just two minutes to relax, wind down, and then I will try and talk about, partial observable settings and also abstraction a little bit at the end. All right, everybody been able to just quickly unwind a little bit? Then I'll continue in a sec. Okay, well, so as I argued, this notion of the Markov assumption is quite strong, right? And so now we're gonna deal with partially observable problems, and those are really problems where this notion will no longer hold. And therefore, in general, we need to have some memory. I'm not gonna go super deep, but I think it's important to see at least then the resulting formalisms. And I then will also try and talk a little bit about abstraction and how these things are related, right? Somehow, if we're dealing with large decision-making problems, we will probably want to apply some forms of abstraction to make them manageable. But that really gets us into this partially observable realm. And I think it's important to be aware about that. Okay, all right. Well, so this is a simple example of a MDP still. Somehow we're say this blue circle, and we're trying to catch the red triangle, right? And we can move left, right, up, down. Perhaps there's again some noise involved. The prey will probably jump around stochastically or something like this. And we can think of the relative position. So 3 to the left, 4 up, as kind of like a description of the state here. And so if we can perfectly observe this, it's just an MDP, right? So now what if we cannot perfectly observe, right? Perhaps there's some range of sites that we have. So that means that in this case, we would somehow observe nothing, right? We don't see the prey. Perhaps if it moves into the line of sight, and we observe it 1 to the left and 1 up. Right, so this is the general idea. There may be many time steps that you now can perhaps is non-observation. And how will you distinguish those? Right, and clearly you're not gonna take the same action all the time for all those non-observations, right? Imagine somehow the prey actually is static, it's just sitting on a particular square. So we don't see it currently. What will be the best strategy? To explore, right? Yeah, somehow perhaps systematically sweep through this grid until we find it. But to systematically sweep through the grid, we need to somehow remember what we did before, right? Somehow we're going to get this non-observation all the time. So somehow we need to remember our own past actions to have an idea of, okay, where did we already look? Right? Yeah. So that's really the thing here. Well, why are many problems partially observable? Usual type of things, of course, like noise. Sensors can be noisy, so this is a noisy version of the bear somehow hidden somewhere. Or perceptual aliasing. That means there's just no way that our sensors could even ever know this, right? So there's something just behind the tree, which we can't notice, right? I don't know what's happening outside this room. My sensors are just absolutely not enough to be able to know what's outside of this room. I don't have X-ray vision, so my sensors are inherently limited in what I can observe. All right. So how can we then formalize these kind of problems? Well, very similar to before, right? Before we had this MDP, states, actions, transition function, rewards. Now we're going to add a set of observations and an observation function, right? And that observation function is going to give us some information about what the true state is, right? So we interact, we take actions, get back to observation, take action, get back observations. But the back end is sort of the same thing, right? Still these transitions that depend on states that govern the world. Okay. So then what kind of policy should we then follow now, right? And I already kind of indicated, well, perhaps we will need to somehow now base our decisions based on what happened in the past, right? So there's no Markovian signal directly available to the agent because it just gets its observations. So somehow it should try and use all the information it has, right? And all the information it has in general would be the histories of the actions and observations that it saw or took, right? The actions it took and the observations it received. That entire history of things. That's all the agent knows. And then, oh, there's something weird going on here. I apologize, but so if we have deterministic policies, we can actually reduce this to exclude the actions, right? Somehow, if we're following a deterministic policy, we can base our decisions on just the history of observations, because then we can somehow, infer what action we actually took, right? If we always, for the same observation history, take the same action, you can just recover the actions that you took. All right. But yeah, of course, you might think, well, can't I really just use this last observation? Well, I think already in the grid world, we saw a kind of clear indication why that wouldn't be possible with just observing none. This is kind of like an example from literature, which is quite famous. And it's a very simple kind of POM-DP. There's two states, 1A and 1B. And the circle around it just indicates that we can't discriminate the two. So this is a problem, a POM-DP, or actually a non-observable MDP, I would say, where there's only one observation, the non-observation, right? You don't observe anything. But if I'm in state A, I should take action B to get the reward R. And then if I'm in B, I should take the action A to get the reward R. Right? If I take the wrong action, I get minus R. That's not great. So yeah, a deterministic policy here, one that always takes the same action, yeah, it might get lucky in the beginning, right? So somehow, if I always take action A, say, and I happen to be in 1B at the start, okay, I get R once, but then I'm stuck here and we'll get minus R forever. Right? Similar for B, I can get lucky if I start here, but then I transition and will get minus R forever. So this is an example where, you really can't have a deterministic policy based on your single non-observation. Right? I can do two things. I can try and randomize or use the history. It's a question here. The question here said, don't we need R to solve this thing? No, we don't. Actually, in a POM-DP, we typically assume that the reward is not observed at all. This is a little bit, it depends a little bit of whether you're in this kind of like POM-DP planning setting or in the reinforcement learning setting. In the reinforcement learning setting, you will need to somehow observe some rewards to be able to do something. But in this kind of like POM-DP planning setting, where somehow, we write down what the POM-DP is, we may not want to observe the rewards at all, typically. We just have the actions and observations, right? In this case, if we would observe the rewards, indeed, somehow that would give us, that would spoil in which states we are, right? It would, reveal what the state was, actually. No, but so our past action does, right? So what, of course, we can do is we can alternate between the actions, right? So I'm going to take A, B, A, B, A, B. Okay, so the action observation history would be A, none, B, none, A, none, B, none, right? I'm not certain what you mean with that. You're saying the action A maps to the same state? Yeah, so what are you... Yes, yes. Yeah, of course. That is very specific to this particular problem. It's just an example of how, by indeed having a history that conditions in this way on your past actions, Actually, you only need to remember the previous action in this one, right? So it's a very simple actually problem. It just shows very clearly that if you take a deterministic policy that maps your observation none to a deterministic action, that you will do really, really bad. And you need some form of history here. Or randomization. You can also do 50-50, randomization of actions. Not as good as alternating, but still a lot better than taking one action always. No, this is a good question. Yes, that is what I said. Let me think about that. Yeah, but if I have this alternating policy, I can just count the number of nones I had and know whether I can still reconstruct my previous action history from that, right? But okay, so perhaps we can take this offline. Yeah. Good. Yeah. Let me continue. Well, the important bit here, I think, is that you realize that in these kind of settings, yeah, really just acting based on the last observation might not be great. Yeah, this is the tiger problems, one of my favorite all-time problems. As an example of a POMDP where you need to, of course, open the door to the treasure, but you don't know behind which it is in advance. And our agent is very limited, so it can open the left door, right door, or do the listen action. It does the listen action, it gets an informative observation. Where somehow it observes, it gets the correct observation, say that here's the tiger behind the left door. If the tiger is behind the left door with 85%. Then somehow the question, of course, is, well, how often would you listen before perhaps opening the door? And what's the optimal policy here? Good. Yeah, let me speed up a little bit. Okay, what can we do to now try and solve these POMDPs? Well, I said, well, if we're going to act based on these histories H, so then we can define this sort of history MDP, right? So this notion of history, this H, yeah, that actually ends up being a Markov signal. And so it is kind of like a state signal. And so we can think of the MDP where the states are just those histories. Right, so we have this model where, yeah, the set of states is now the set of histories. This is what I try to convey here. And then, of course, you can write, again, these value functions that we saw before, right? So we're going to get Q of H and A and V of H, etc. Right? It's just same Bellman equations, Bellman optimality equations that we saw before. Right, of course, how is RH A and also, the probability of a next H prime given current H really defined? Well, there's some expectations over those underlying states going on there, right? Because those are the ones that in the end drive the actual dynamics. So, well, for instance, in order to predict what is the expected reward for some history H, and then taking an action, the actual reward is generated by RSA, right? So we need to somehow have then the probability of the underlying state S given the history H, right, to define this. Yeah. Okay, so this now also more or less directly gives us a way to possibly solve these things, right? Well, like I said, like we discussed, this tree concept actually is sort of general. So somehow, yeah, we can still do that lookup tree construction and try and do now this dynamic programming over this tree. That still works, right? And then, of course, that tree will be huge again, but somehow some of these things, like Monte Carlo tree search, you could apply to these kind of trees, right? And people have. Can we do something else? Well, it turns out that in these POMDPs, yes, actually, that space of histories might be unwieldy. What we can do is try and retain beliefs, right? So the basic idea is just, we don't want to treat all these histories very differently if we think that somehow they lead to the same distribution over underlying states. Right? It was that distribution over underlying states that we needed to predict the reward and also the next state transition. Those are really the things that kind of like should matter. Okay, right, so indeed, to predict, so if we're at the last time step of the horizon t problem, so the last time step is t minus 1, then the expected reward for that particular history at the time step and an action is going to be just the immediate reward for ht minus 1 and that action, and that is indeed, that expectation over the underlying state. What we just said. And this notion, that's essentially what this belief is, right? The belief over the underlying state given the action observation history that we've seen. And it turns out that that is sufficient to define, therefore, that value, right? So here, all I'm using to predict that value is just that belief. And so you can generalize that. You can show with your backwards induction that actually, this belief is a sufficient statistic for predicting the value in your entire POMDP. Right? So we can define now these belief states. Typically, people write them, with B. So it's really defined as the posterior distribution of the states given the full action observation history, B. And then you can write these value functions in terms of B. And it turns out that you can actually also recursively update the belief, of course, now. So really you can get rid of that history completely. You don't need to store it. You have your previous belief, you do an action, you receive an observation, you update your belief, and then you're good to go again. Right? Okay, so that's nice. And so then you can also now use somehow these beliefs to try and think of solving this POMDP. It's a question. Yes, well, this is a very good question. So somehow, if your initial belief for some reason was really off in a way, right? Then what would happen? Well, that is something that we really cannot really fix, right? Somehow, if your initial belief excludes, does not put any positive weight on somehow the true state of your system, you really believe that you are in some alternate reality, somehow, I don't know. Yeah, I don't have a good example, but if I believe I'm actually not here, but I'm still in the train or something, I really believe this, then I'm going to take, very different actions, right? In the action taking, you mean? Well, yeah, so I'm not certain even if that would fix it, right? Like, so somehow the idea here is that we're just going to use a Bayes rule to update our beliefs in a Bayesian way. And in the end, if somehow our initial belief, did not put any positive mass on the true state of the world, we just risk that it's a misspecified learning problem, and there's no randomization of actions that will necessarily fix that. It is a Bayesian approach in the end, right? There's an initial belief that you're gonna end up updating. There's no real fundamental fix for this, perhaps, I don't know. So Peter Groenwald did some work on Bayesian updating in misspecified models. And they had some kind of adaptation, I think, of Bayes' rule where somehow they showed that then, at least in some linear cases, they could converge to the best in class sort of belief. the extent to what that really generalizes to these kind of settings, I am uncertain about. I should have. Well, good question, certainly. Yeah, let me try because okay, I'm gonna kind of skip this, right? So somehow what you can end up doing is try to plan now over these continuous belief spaces by somehow retaining like vectors, right? So somehow in the tiger problem, the belief that our state is right is on the x-axis. So here we believe that the state is right. So we should open the left door, and that induces then a vector over this space. You can now somehow exploit this structure of this function to try and do, value iteration in this belief space, if you will. But I'm not going to go in any more details. I want to somehow at least make the link to this abstraction still clear, because that's also what we will be working with a little bit in the tutorial. Okay, yeah, so this summarizing, many problems actually are partially observable, of course. And then, we might need to condition on histories or somehow might want to compute these beliefs. And then adapt somehow these solution methods. All right. So abstraction is when we don't want to observe the full state, essentially. Yes, questions?
Clarification. So these are probability distribution, right?
Yes, probability distribution over the states.
Then, like, when the function becomes like the transition from one probability distribution to the other, right? So instead of using, the space is the space of probability distribution over.
Yes. Yeah, so given a particular belief and an action and an observation, you can deterministically compute the next belief. Right? So the probability of jumping to that next belief is essentially the probability that after the particular action, you get that observation. Right? And a little bit more subtle, because you could also perhaps take a different action and then get a different observation that would lead to that same belief. But yeah, essentially, that's what it boils down to. All right. Many MDPs are really large, right? I guess this is now not moving indeed. But the idea is that, even if we're dealing with a very complex world, right? So here on the left-hand side, this is a traffic control problem with many intersections that perhaps we would want to deal with. And then on the right-hand side, we just zoomed in on one of these intersections because, perhaps we just want to, make the problem more manageable, abstract away to some extent the rest. All right. So, this idea of applying state abstraction is essentially a function, that takes in the true state and maps it to a now more abstract state. Right, and of course, that seems like a good idea, and generally often it is, right? If you can come up with good abstractions, you can make progress on problems. I think this is what we humans do all the time. It's actually one of the bits where perhaps we are still ahead of ChatGPT, etc., right? Kind of like formulating the right level of abstraction to tackle a particular problem. That is actually not so easy, figuring out which abstractions you should take. But it's quite important to make progress. So how can we really think now of abstraction in these MDP kind of contexts? So essentially, I like to think of them in this way, where all the dots correspond to true states of the world, right? And somehow we're saying, well, some distinctions don't matter anymore, so we're partitioning this set of states into clusters, and then the clusters correspond to these abstract states, right? And of course, how you should cluster and partition, that's not always clear. It might be very difficult. But then there's kind of like different types of abstractions that people have tried to think about. I will, in the also interest of time, not go through all of them. But yeah, somehow you start, say, from the identity function. So there's no abstraction. Every state is just its own state, its own little cluster. And then, you can get these increasingly coarse abstractions. So somehow we can have model irrelevance. This should not be indented, by the way. I don't know why that happens. These are not instances of model irrelevance. These are just different abstractions. I apologize. Model irrelevance means, well, the reward function will be preserved and the transition function will be preserved. And that means you're really capturing everything, right? Kind of like what we did with this POM-DP as well, with the histories, right? Like, as long as the transitions you can predict and the rewards you can predict, you actually have a lossless abstraction. But you can, even try and have coarser abstractions up to the point where you cluster together all the states that have the same optimal action. Of course, how you get such an abstraction is not so clear. That's some of the result of your planning normally, right? So, because you need to compute the optimal policy. But yeah, so you have this kind of hierarchy from very fine, no abstraction to increasingly coarse abstractions. Is the idea. Well, if you have such an abstraction, you can now construct an abstract MDP, right? What does that mean? Well, we essentially take our clustering and just turn it into now an abstract MDP, which has these discrete states corresponding to the clusterings. And then we need to somehow define the transitions and the rewards for those clusters, right? And in order to do that, we're going to use this kind of weighing function that's just essentially going to specify for each cluster some arbitrary distribution over the states in it. Right? You could take one prototype or put uniform weight on all the states in a cluster, something like that. There's different choices that you could make. That will lead to different results. But of course, the hope is that if your abstraction is any good, that it doesn't matter so much. Right? That's kind of like the basic hope here. So, for instance, if you have an epsilon model similarity abstraction, right, something where the model is approximately preserved, then you can show that the value loss of planning in now this abstract MDP versus the true one is bounded, the performance loss that you get. So that's nice, right? But then, yeah, this thing also is very much like a POM-DP, right? Because, well, in the POM-DP, we had actions and observations coming back. Essentially, now these abstractions are like observations, right? So we will observe the cluster, but not the state in the cluster anymore, say. Right? And so when we now enter a abstract state, there's a true distribution over the states in that environment now corresponds to this belief, and it would depend on the real history, right? So there's kind of like conflicting message going on here, where we just saw POM-DPs, and we said, well, we really need to condition on the history in order to do well. And now, on the other hand, we're considering state abstraction, and we're saying, well, we'll just act based on that abstract state, right? On the latest observation of that abstract state. We're not retaining any history of abstract states, just acting based on this abstract state. So, like, well, couldn't this then be very bad? Because we just saw an example in the POM-DP case where, the myopic decision making is very bad. And of course, the thing that kind of like takes away this perceived paradox is about this abstraction quality. So if the abstractions are good, then this myopic decision making can be good. If the abstractions are very, very poor, like the abstraction we saw earlier, well, somehow we had this two-state MDP and we were just getting one non-observation. That was not a great abstraction, so to say, right? Okay, all right. Well, yeah, so here, this weighting function essentially approximates the belief that we would have, right? And so if that is a good approximation, a different way of thinking of it. If that constant approximation actually is a good approximation of any belief I could have when revisiting that abstract state, then we might be doing quite well. Okay, yeah, an abstract MDP that we construct is an MDP, right? Because we construct it. We construct the MDP. We have the original MDP model. We have the abstraction function. Then we define the weighting function, and we construct this abstract MDP. And it's an MDP, therefore. But somehow also it's important that, that MDP cannot be experienced. Right? So if I'm actually going to move to a reinforcement learning setting where I'm interacting now with the world through somehow my glasses, where I only see these abstract states, of course, in that case, my observations, everything will be generated by the underlying state of the system, right? I'm actually interacting with the MDP, not with this abstract MDP. I can't interact with that abstract MDP because it just only exists in my imagination, essentially. Okay. And that's important because that means that if you apply some reinforcement learning techniques to these kind of abstract MDPs, or you're thinking you're doing that, you may end up assuming that particular guarantees might hold that actually don't hold. I'm very happy to talk about that. I had a paper with a student of mine on that topic 2 years ago. I think it's kind of nice. It goes a little bit beyond what we can do now. I'm hoping to cover that in my talk for Tuesday in the workshop. I'm not certain if you will attend it. But yeah, I still need to construct the talk, so we'll see. Okay. Yes. So let me wrap up here. We've been looking at stochastic decision-making and how can we compute plans, explaining this generalized policy iteration framework, and then also talk a little bit about what I think is really important if you're gonna try and apply these things in the real world, namely partial observability, because very few problems will really have that Markov property, and the idea of abstraction, which somehow makes clear that, okay, so you might be able to get away with it, but indeed somehow what you define needs to be good enough, right? So the Markov property might not hold exactly, but there's some criteria under which it can still work. So it somehow needs to be good enough. Okay, well, that's all I had, I think, to tell today. Here's indeed a policy evaluation example in more detail, but you can have a look at that. Thanks for your attention.